right, good afternoon, everybody. Thanks for coming by today to check out our final senior design project, the inVigo glasses. We know today's been a jam-packed day full of exciting engineering technical presentations, and they've been exciting, but it's also been a long day. And we understand if you're starting to become a little bit drowsy, a little bit sleepy. If you are, not to worry, we created a product that's perfect for you. So, my name is Karabinos. This is Blake Winston, Jason Yee, and Jonathan Kern. And our senior design project was designed to use simple non-imaging infrared sensors to track your blinking patterns over the course of the day, and to determine when you're becoming drowsy before it becomes a problem, and then to alert you, and to also send a signal to your phone or your mobile application to help you not only become alert, but also regain your attention as well. So, just to give you a quick overview of what we're going to talk about today. First, we'll talk about the problem that we were addressing, unintentional drowsiness. We'll talk about the solution that we came up with. We'll break down the design, the individual components of these glasses. Then we'll put them all together and show you how they all fit into one cohesive unit. And then we'll show you a live demo, what's going actually on inside these glasses. And then we'll talk about the future and what's next in terms of commercialization and in terms of improving this design. So, the problem, unintentional drowsiness. We think it's pretty much everywhere. In terms of the students' perspective, we know that if you sit through a boring lecture, if you sit in the library for too long, you start to lose your attention, you start to lose your focus, and that's the problem, from a student's perspective. But we also know that it's a problem in terms of driving. Drowsy driving is a significant problem, probably the biggest industry or probably the biggest potential market that these glasses have. There's some pretty alarming statistics. You can see about 37% of people had actually fallen asleep at the wheel at some point. Drowsy driving leads to over 1,500 deaths per year. So it's a very significant issue, and we'll look at the current state of the art about how driving companies or how car companies are solving this problem with imaging sensors. It's also a problem in certain professions where people perform very monotonous tasks over long periods of time. We thought about sentry workers. We thought about security guards. We also looked into it. We also found out that surgeons have problems with drowsiness because when they're over a surgery table for extended periods of time, they tend to kind of lose their attention and lose their focus. And that was a little frightening to think about in terms of if somebody's got a surgery for being performed when some of your doctors falling asleep. That's a big problem. So the solution that we came up with these simple non-imaging infrared sensors to detect blinking patterns. But what I mean by non-imaging is they actually just shine a soft IR LED light on your eye, and we measure the amount of infrared light that's reflected off of your eye. We'll look into that a little more in detail in a second. The current state of the art and what car companies use are imaging sensors that are built into the dashboard of your cars, and they actually take pictures of your eyes, which is very reliable, very proven, but it's also very expensive. These sensors are very bulky. They need to be mounted down, and we wanted to come up with a way to have a design that could be mobile, that could be still reliable, still efficient in keeping you awake, but also something you can take with you wherever you go. So that's why we came up with these simple non-imaging infrared sensors. We wrote a custom algorithm to detect when you're falling asleep before you actually fall asleep, because that's when obviously it becomes a problem when you lose your consciousness and you actually fall asleep. We have these embedded coin motors that are built into the frame of these glasses, and those stimulate you kind of like a cell phone, send a soft vibration through the glasses to help you wake up, and then we also send a digital signal to your Android phone or a tablet, and that can help you provide additional alerts. We can visualize the data for you on this application, and we can also store drowsy statistics that we'll talk about a little bit in the future as well. So now Blake's going to talk quickly about the circuitry that we designed for these glasses and how we go about collecting the data that we analyze.
Thanks, Drew. So the fundamental concept behind our glasses is that when your eyes are open, they reflect less infrared light than when your eyes are closed. So to take advantage of this, we used an infrared LED to transmit an infrared signal and an infrared phototransistor to take that signal back in. And this registered as a voltage difference that allows us to detect blinks and observe patterns in people's blinking. So this was kind of the first step in designing this and designing our glasses, was proving this concept worked. And then once we did that, the next major step was finding a way to gather a clean signal. And by that I mean a signal that's been filtered for whatever ambient IR light is in the room or setting that you're in, so that we can have a consistent, clean signal to analyze. So the way we did this was we transmit a modulated infrared signal generated by an M2 microcontroller through the infrared LED at a carrier frequency of about 1,000 hertz. We then take that signal in through the phototransistor. It's then passed through a bandpass filter to isolate the data that we have transmitted. It's then amplified using an op-amp, and then the signal is then returned to a regular voltage-like signal using an envelope detector. So that was the process we went through to get to where we can begin collecting data on different users, collecting data in different environments, and ultimately, designing our final product. So now John is going to talk a bit about how we implemented this mechanically.
Thanks, Blake. So to implement everything together, we started off by prototyping. One of our initial concerns was actually the IR safety and making sure it was an IR LED that complied to industry standards. So we reached out to a Raytheon technician, as well as we met with a laser safety specialist here at Penn to make sure that we were using an IR LED that is user safe. Another issue we had was in our early prototypes, we had an IR module that was fixed in place. So we realized that maybe it would work on Drew and I, but it wouldn't work on Blake and Jason. So we quickly decided to create something that was one size fits all, something that would work for all users. To do this, we created, as you can see, the plastic piece here, which was laser cut, has 2 degrees of freedom, so that the user can adjust it perfectly during a calibration mode that we have. Once it's calibrated, the user leaves it alone, and he can go about his day, and it should stay in place, and it does. Next, we'll show you one of our early prototypes. This is our prototype I was talking about with a module that's fixed in place. And it also has a large, bulky circuit board that's not integrated. So this was a proof of concept. The next one is the one I have in my hands, which is finally we integrated everything together. It's a bit large and bulky, but it works. And finally, we have what the new sleek design, lightweight, and a lot nicer, the one that Blake is wearing over here. Next, during prototyping, we collected a lot of data. Drew will talk to you a little bit about what we do with that data.
Thanks, John. So once we had this functional prototype, the next thing we did is we went around engineering. We put these glasses on as many people as that would try them on. And as you can see here, we have only 6 users, but we have a big collection of data. We're still in the process of analyzing this data because it helps us to keep refining our algorithm. But the first goal we found was just finding these general patterns that emerge. And as you can see, this is user data from 2 different people. You can see there's some of these alert blinks. You can see this quick waveform of those alert blinks. You can see some of those drowsy blinks that happen. There's kind of an extended sleep period here. And all we did was we asked these users to listen, blink normally, and then start blinking like you're drowsy, and then fall asleep, basically. And what we did is we videotaped them. We compared the video to these signals, and we started to get a feel for the patterns that emerged. So we still hadn't written anything in terms of algorithm yet. This was more to understand what type of data will we be collecting. Then we went to see if there's any data that's published already. Has anyone else looked at these drowsy statistics? And what we found was there are some reports about mean blinking parameters that we found that are published and that are proven. So one report we found showed that there's statistics on the average blink duration. There's also statistics about the time that it takes you to close your eyes and the time that it takes you to reopen them. What we thought originally was that a blink was pretty symmetric. We thought that those times would be pretty equal. And what we found is what you can see here by this top graph is that it's actually not. When you're alert, you take a lot less time to close your eyes than you do to reopen them. And it happens so fast you probably don't realize it, but that's what this report showed. So we wanted to explore that concept a little further. Well, what proportion of the time does it take you to close your eyes compared to when you reopen them, when you're alert and then when you're drowsy? So this is back to our user data. We took a closer look, and what we found was we found some trends that emerged. As you can see here, it's kind of a small little wave here, but this blink on the left, that quick blink, is an alert blink. And that blue time, that blue shaded area, is the time that it takes you to close your eyes. And if you look pretty closely, you can see that it's about, I think the published statistic is about 40% of the blink duration is how long it takes you to close your eyes, and that matches pretty closely to the data that we were able to find. But then what we found, and what was interesting to us, was when people become drowsy, the time that it takes you to close your eyes actually becomes significantly longer relative to the total blink duration. And that becomes more and more apparent as you become more and more drowsy. So you can see here's a drowsy blink. Not only did the duration increase, but the time that it takes you to close your eyes is a lot longer. And that makes intuitive sense if you think about it. if you simulate kind of a drowsy blink, you kind of close your eyes slowly and then you pop back open real quick. That's the statistic that we were tracking with our algorithm. We call it the blink closing time ratio. And the goal then is you can see some alert blinks here on the left. You see these drowsy blinks that precede somebody falling asleep. We want to be able to find these drowsy blinks before somebody actually falls asleep, then alert you, then send this signal to these embedded coin motors, send this signal to your phone, do everything that we can to wake you up, because once you fall asleep, that's when all these alarming statistics happen. So that's kind of how our algorithm works. Now we're going to go ahead and we'll show you a quick picture of how everything works together. So now, just quickly, to recap, Blake talked about the circuitry involved. You can see the circuit board here on the right. Jonathan talked about the design challenges that we face in terms of this IR module and focusing it on the right point of your eye. I talked a little bit about the algorithm, and you can see the N2 microcontroller, and then the batteries and the coin motors are on the left. And then the biggest design challenge is putting that all together into the current prototype that we have now. So, now let's show you in real time what we're actually talking about. So, as we were talking about before, this is a live feed of the voltage that's going across the IR that we're measuring going across Blake's eye right now. This is also displayed on this Android application that we wrote. So basically, this screen is showing what's going on this Android application. It's a cool visual way to see your blinking patterns. So you can also track, you can also see that we're counting how many times Blake is blinking. So over the course of this last 10-minute presentation, Blake has blinked 468 times. So that's pretty cool. We can do a lot, I think, in terms of like the average blink. There's a lot of parameters that we can keep track of like that. So, Blake, if you can, why don't you show us 5 quick alert normal blinks, and we'll see what it looks like on the screen.
All right, so here's 1, 2, 3, 4, 5.
Great. So now you can see nothing actually happened. These glasses do not alert you if you're alert, obviously. They don't send any kind of signals. But you can see that now the wave is going, but it was pretty short, pretty symmetric. That is not an alarming wave. So now, Blake, why don't you simulate drowsiness? Let's see what happens when you're about to fall asleep and see what happens, see if our glasses can pick those up. So now you can see just what we were talking about before. We picked up a drowsy blink. We can see that time that it takes him to close his eyes is a more significant portion than the overall wave. So now you can see 1, 2, and now we're vibrating. So now you can see the glasses found consecutive drowsy blinks. He hasn't fallen asleep yet, but he looked like he was about to. So we sent an alert to the glasses. They started vibrating, and now he's back awake. So we also do have a fail-safe, though, just in case Blake were to instantly fall asleep and not exhibit any of these drowsy blinks. And that is him closing his eyes for an extended period of time, which you can see now that the glasses have realized, all right, so he's not asleep. He also got that little stimulation, and now he's back awake. So that's the way that these glasses work. There's 2 things we're looking for: consecutive drowsy blinks, and then if he's actually fallen asleep. But now that we've realized how much data that we can gather from these glasses, I think instead of clicking to the next slide, Blake, why don't you go ahead and blink us to the next slide? No, none of us, this is not a magic trick. None of us are going around here. So now Jason's going to talk quickly about what's next in terms of commercialization and in terms of Android development.
Thanks, Blake. So what you saw just now is how the thanks, Drew. So what you saw just now is how the inVigo glasses are right now. Going forward, we would like to further develop our current design. We hope to further redesign the inVigo glasses so that they can clamp onto any pair of glasses, whether they be sunglasses, reading glasses, or goggles, by using a clamp design so that it can clip onto the side of the frames. We also plan to further miniaturize the circuit. Right now, the circuit, even though it's a lot miniaturized, we believe we can still make it smaller by using custom components, such as using a custom PCB board, using a different microcontroller, and smaller Bluetooth module to further size down the inVigo glasses so that they fit more comfortably on the users. We also plan to add in more sensors, such as an accelerometer, so that it can measure head tilt, and combine that with the blink data to further be able to determine whether or not a user is falling asleep. So Blake, why don't you continue blinking us to the next slide? Okay. Yeah, so we've developed an Android app, which you just saw right now. The Android app can vibrate in conjunction with the glasses so that you can have your Android phone or tablet vibrate when you're falling asleep. So we have the glasses using a Bluetooth module to send these commands over to the Android to tell it to do things like vibrate. And we can further develop that so that we can have the Android app play a sound, for example, or we could have it pop up a little mind puzzle when it detects that you're falling asleep, maybe have Fruit Ninja popping up so that you play a little game to wake up. Or we could even have it randomly call someone from your contact list, like maybe your boss or your mom, for example. And that's definitely a good way to keep you awake. In addition to that, we also plan to put in more analytics. Right now, you see that the app can keep track of how many blinks you've had over a certain period. We'd also like to keep track of like how many times you've fallen asleep over the day, what are the times you usually fall asleep, and what are the cases where you might fall asleep, like whether it's during while you're driving, or maybe it's when you're in thermodynamics class, for example. I sort of indulgence John just now. No offense. And so we'd also like to have the user be able to use the app to tweak certain parameters with the glasses. For example, right now we have the glasses vibrating after 3 drowsy blinks. If you're in a really sensitive environment, such as driving, you might want the glasses to vibrate after 1 drowsy blink. And so we'd like to have the Android app be able to have the user change these parameters to further tweak the settings for the glasses. That's a lot of things you can do with Android. We think the possibilities are just endless with what we can do.
So that basically concludes our presentation. Thanks for coming by today and learning a little bit more about the inVigo glasses. We're excited about what we developed, and we're excited about where this product might be able to go in the future. So now we'd like to open up the floor for any questions.
Questions now.
No questions.
See you at lunch.
All right. See you soon.
Okay. Thank you.